السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على أشرف الأنبياء والمرسلين سيدنا محمد وعلى آله وصحبه أجمعين. This is a video recording for the physiology lecture on the electrocardiogram, the ECG, in the cardiovascular block. These are the active learning objectives, the intended learning outcomes, the ILOs for this learning activity. And here we have the recommended learning resources for this lecture. The electrocardiogram, the ECG, or the EKG as the Americans say, is a record of the electrical activity of the heart from the surface of the body. We mentioned in the previous lecture, in the lecture on the electrical activity of the heart, that the sinoatrial node, the pacemaker of the heart, generates rhythmical electrical impulses, which we call them the cardiac impulses, and these rhythmical electrical impulses are conducted through the specialized conduction system of the heart, and also from cell to cell directly through the gap junctions in the intercalated discs, in order to stimulate and excite the myocytes in the atria and the myocytes in the ventricles. And when these myocytes are stimulated and excited, they respond electrically by generating fast response action potentials in their sarcolemma, and these action potentials propagate through the sarcolemma and also through the tubular system. So it is thus clear that the heart functions as an electric generator, and the electrical activity generated by the heart is transmitted to the surface of the body, because the tissues of the body are good electrical conductors, since they contain electrolytes, and then it is possible to record the electrical activity of the heart from the surface of the body. So here we have the heart, and we can look at the heart as if it is an electric generator, as a battery, and we can record the electrical activity of the heart, which is transmitted to the surface of the body using a galvanometer, a voltmeter. This is an electric device which records and measures the electrical activity. It measures the voltage. And we need to have electrodes to close this electric circuit so that we can measure and record the electrical activity of the heart from the surface of the body. Now a very important question arises, which is, what is the difference between recording an action potential and recording the electrocardiogram? The ventricular action potential is recorded from a single myocyte using an intracellular electrode. So when we record the action potential of a single myocyte, we need to insert a microelectrode into the cell, and we place it just very close to the inner surface of the membrane, and the other electrode is placed on the outer surface of the membrane, and the two microelectrodes are connected to a galvanometer. In this case, we record the action potential from a single cell. While in recording the ECG, the electrocardiogram represents the summed electrical activity of all cells in the heart, and we record this summed electrical activity from the surface of the body. We shouldn't insert microelectrodes into each and every myocyte. So we record the electrical activity of all cells of the heart from the surface of the body. Again, we need to have a galvanometer. We need to have an ECG machine, which is nothing but a modified galvanometer, and we need to have electrodes to close the electric circuit. Thus, if a recording electrode is applied on any point on the surface of the trunk, and this recording electrode is connected to a galvanometer, it records the electrical activity of the heart. It will detect electrical waves reflecting the electrical activity in the heart. These electrical waves may be as small as 1 millivolt, and thus we can amplify them in order to see them well, and we can record them on an ECG paper or on a monitor or on a computer, and we can store them. You need to focus on these electrophysiological facts related to recording an electrocardiogram. The first fact is that a positive wave, a wave above the isoelectric line, is recorded when the polarization is propagating towards the electrode, or when repolarization is propagating away from the electrode. On the other hand, a negative wave is recorded. A negative wave is a wave when the ECG machine needle moves downwards below the isoelectric line and then returns to the isoelectric line. So a negative wave is recorded when the polarization is propagating away from the active electrode, or when repolarization is propagating in the direction of the active electrode. And when there are no propagating potentials, no waves are recorded, and the recording needle will remain on the isoelectric line, on the line of the zero potential, which is known as the isoelectric line. For recording an ECG, we need two electrodes, as we mentioned in the previous slides, in order to close the electric circuit. One of the electrodes is the active electrode, which is also known as the searching electrode or the exploring electrode. And this electrode, the active electrode, is applied to a recording point on the surface of the trunk and is connected to the positive end of the ECG machine, the modified galvanometer. The other electrode is the reference electrode and serves as a reference to the active electrode and connected to the negative end of the galvanometer. So here we have this part is depolarizing, because the inner surface of the membrane is positively charged and the outer surface of the membrane is negatively charged. And as you can see, depolarization is moving towards the active electrode. This gives a positive deflection. So the needle of the ECG machine moves up and then returns back to the isoelectric line, giving a positive deflection, a positive wave. So a positive wave is recorded. Positive wave is a wave above the isoelectric line when the polarization is propagating in the direction of the active electrode. Now, what has happened, now this part is repolarizing because the inner surface of the membrane is becoming negatively charged and the outer surface is now positively charged. And we have repolarization moving towards the active electrode. This gives a negative wave. The needle of the ECG machine moves down the isoelectric line and then returns back to the isoelectric line. So where on the trunk we can place the active electrode in order to record the electrical activity of the heart? We can place the active electrode on a very large number of points on the trunk. However, by convention, we record the electrical activity of the heart from the surface of the body. We record the ECG from 9 standard points on the surface of the body. 6 of these recording points are located on the chest wall, and the remaining 3 points are on the limbs. Here we have the 6 recording chest points, and we call these chest points V's. So we have V1, V2, V3, V4, V5, and V6. V1 is at the right fourth intercostal space near the sternum. V2 is at the left fourth intercostal space near the sternum. V3 is midway between V2 and V4, so we need to define what is V4. V4 is at the left fifth intercostal space at the mid-clavicular line, at the apex of the heart. V5 is at the left fifth intercostal space at the anterior axillary line, and V6 is also at the left fifth intercostal space but at the mid-axillary line. You must have known from anatomy that the heart has an anterior surface formed by the right ventricle. This is the anatomical position of the heart in the chest cavity. We have an anterior surface formed by the right ventricle, and we have an anterolateral surface, a surface which is anterior but is also facing laterally, and that's why we call it anterolateral surface. This anterolateral surface is formed by the left ventricle, and we have an inferior surface or a diaphragmatic surface formed by both ventricles. This is the body, and if we take a cross section through the heart, through the ventricles, we will see that the right ventricle forms the anterior surface of the heart, and the left ventricle forms the anterolateral surface of the heart. And the V1 and V2 chest points face the anterior surface of the heart. V5 and V6 face the anterolateral wall of the heart, and V3 and V4 face the septum. So they face the anteroseptal portion of the heart. So if the active electrode is placed at V1, the active electrode would be recording the electrical activity of the anterior wall of the heart. Similarly, if the active electrode is placed at V2, it would be recording the electrical activity of the anterior wall of the heart. If it is placed at V5 or V6, it will be recording the electrical activity of the anterolateral wall of the heart. And V3 and V4 will be recording the anteroseptal. So what about then the electrical activity of the inferior surface of the heart? In addition to these 6 chest points, V1 to V6, we have three limb points. We also call them V's. So we have VL, VR, and VF. VL is at the junction of the left arm with the trunk, and any point on the left upper limb has the same potential. And if we place the active electrode at this is VL, and any point on the left upper limb would have the same potential. So if we place the active electrode here at VL, the active electrode would be facing the anterolateral surface, or the anterolateral wall of the heart would be facing the left ventricle. So point VL is also an anterolateral point together with V5 and V6. VR is at the junction of the right arm with the trunk, and any point on the right upper limb would have the same potential. So this is VR. VF is at the junction of the left lower limb with the trunk, and any point on the left or the right lower limbs would have the same potential. So this is the VF here. So when we place the active electrode at point VF, the active electrode would be facing the inferior surface of the heart. So we have finished with describing the locations of the recording points, the 6 chest points and the 3 limb points. And now let's see what we get when we place the active electrodes at these specific recording points, and we ask the ECG machine to show us the record of the electrical activity of the heart. And this is what we call the ECG leads. So an ECG lead is the ECG record. It is the actual record obtained on the ECG paper as it comes from the ECG machine, or on the monitor or on the computer when the recording electrodes are placed at specific points on the body. How many ECG leads we can have? We can have 12 ECG leads. 9 of these 12 ECG leads are unipolar ECG leads, and the remaining 3 leads are bipolar leads. So what are the unipolar ECG leads? The unipolar ECG leads are the ECG records which are obtained when the reference electrode is kept at 0 potential, and the active electrode is applied to one of the 9 recording points on the surface of the trunk, from V1 to V6 and VL, VR, VF. So we can have then 9 unipolar ECG leads. How can we keep the reference electrode at 0 potential? This is a long story, and you need not to worry about this. All what you need to know is while recording the unipolar ECG leads, the reference electrode is kept at 0 potential and is connected to the negative end of the ECG machine, and the active electrode is applied to the recording points and connected to the positive end of the galvanometer to the ECG machine. So, as I've just mentioned, we can have 9 unipolar ECG leads. 6 of these 9 unipolar ECG leads are unipolar chest leads, which are recorded from the 6 standard chest points, and they are designated as also the leads. We call them V1, V2, but now lead V1, lead V2, lead V3, lead V4, and V5 and V6. The remaining 3 unipolar ECG leads are unipolar limb leads. These are recorded from the limb points and designated as lead VL, lead VR, and lead VF. However, the voltage which is seen in these unipolar limb leads is usually small, and we need to amplify the voltage, we need to augment the voltage in order to see the recording well. And this is done by adding a resistance, because when a resistance is added, the voltage increased according to Ohm's law, and the augmented leads are now known as AVL, AVR, and AVF. So the unipolar ECG leads, again, we have 6 unipolar chest leads designated from V1 to V6. V1 ECG lead is when we place the active electrode at point V1 and the reference electrode is kept at 0. And the same description applies to the other unipolar chest leads. So leads V1 and V2, they record the electrical activity from the right ventricle, from the anterior wall of the heart. And leads V5 and V6, these unipolar chest leads, they record the electrical activity of the anterolateral wall of the heart formed by the left ventricle. And leads V3 and V4, they record the anteroseptal activity. So we call V1 and V2, these are strict anterior leads. V3 and V4 chest leads, these are anteroseptal leads. V5 and V6, these are anterolateral leads. The unipolar limb leads, the AVL lead is recorded when we place the active electrode at point VL and the reference electrode is kept at 0. So now the active electrode is also facing the anterolateral wall of the heart. So lead AVL is also an anterolateral lead together with leads V5 and V6. Lead AVF is recorded when we place the active electrode at VF and the reference electrode is kept at 0, so the active electrode is facing the inferior surface of the heart. So lead AVF is an inferior lead, and this is the first inferior lead which we have described so far. So we have finished with the description of the 9 unipolar ECG leads, and there are 3 additional ECG leads which are bipolar ECG leads. The bipolar ECG leads are obtained when the active electrode is applied to a recording point and the reference electrode is also applied to another recording point. So unlike the unipolar leads, the reference electrode is also applied to another recording point in the bipolar ECG leads. So the ECG will be then a record of changes in the electrical potential at the active electrode relative to the reference electrode. We have 3 standard bipolar leads. We call the standard bipolar leads lead 1, lead 2, and lead 3. Lead 1 is different from lead V1. Lead V1 is a unipolar chest lead, while lead 1, this is a bipolar limb lead. Lead 1 is recorded when we place the active electrode at VL and the reference electrode at VR. So it records the potential between the left arm and the right arm. And lead 2 is recorded when we place the active electrode at VF and the reference electrode at VR. Lead 3 is recorded when we place the active electrode at VF and the reference electrode at VL. So the active electrode is facing the inferior surface of the heart. In lead 3, similarly in lead 2, the active electrode is facing the inferior surface of the heart, while in lead 1, the active electrode is facing the anterolateral surface of the heart. Thus, lead 1 is an additional anterolateral lead, while leads 2 and 3 are additional inferior wall leads. So the inferior wall leads are AVF, lead 2 and lead 3. The strict anterior leads are V1 and V2. The anterolateral leads are V5, V6, AVL, and lead 1. And the anteroseptal leads are V3 and V4. The bipolar limb leads can be looked at as if they are electric vectors. So this is the electrical vector of lead 1. A vector has got a value in magnitude and a direction, and this is a vector of lead 2, and this is the vector of lead 3. So this is the vector of lead 1, and this is the vector of lead 3, and this is the vector of lead 2. So it looks that the magnitude and the direction of vector 2 is equivalent to the sum of vectors 1 and 3, because this is the direction of the vector of lead 1, this is the direction of the vector of lead 3, and this is the direction of the vector in lead 2. So in the ECG at any given instant, the potential of any ECG wave, the waves of the ECG will be described later in the lecture. The potential of any wave in lead 2 is equal to the sum of the potentials of the same wave in leads 1 and 3. Because the vector again of lead 2 is equal to the sum of the vectors of lead 1 and lead 3. And this relationship was first described by Einthoven, and we have a law in the ECG known as Einthoven's law. This law states that at any given instant, the potential of any wave in lead 2 is equivalent to the sum of the potentials of the same wave in leads 1 and 3. So the voltage again of any wave in lead 2 is equal to the sum of the voltages or the potentials of the same wave in leads 1 and lead 3. So if the electrical potentials of any two of the three bipolar limb leads are known, the third one can be determined mathematically using Einthoven's law of the ECG. This relationship is also used to make sure that our ECG connection and the placement of the electrodes which we made while recording the ECG are correct. So if we measure the voltage of a particular wave in lead 2 and we measure the voltages of the same wave in lead 1 and lead 3, and we find that the voltage of that wave in lead 2 is equivalent to the sum of the voltages of the wave in leads 1 and 3, this means that our ECG connection and the placement of the electrodes are correct. So having described the ECG leads, the unipolar ECG leads, and the bipolar ECG leads, and having known that we can have 12 ECG leads, 9 of them are unipolar leads and 3 are bipolar leads, let's see how the ECG is recorded, how these ECG leads are recorded. We can record each ECG lead separately, but this will not be convenient for the patient and it will take long time to record the ECG. So what we actually do in practice, we place the active electrodes at all the 9 recording points on the body, and we press the ECG machine and the ECG leads will come out of the ECG machine, or the ECG leads, the 12 ECG leads will be displayed on the ECG paper as the paper comes out of the ECG machine, or the 12 ECG leads will be displayed on the monitor or on the computer. So this is what we do when we record an ECG. The ECG leads, the actual records which we see, are composed of waves, ECG waves, and ECG intervals, and ECG segments. And for simplicity, let's record only one ECG lead and identify the ECG waves and intervals and segments. And let's record the AVL. And when we record the augmented VL, remember AVL is a unipolar limb lead. So the active electrode is placed at VL and the reference electrode is kept at 0. The active electrode is connected to the positive end of the galvanometer, and the reference electrode, which is kept at 0, is connected to the negative end of the galvanometer. So when we have the polarization moving towards the active electrode, this will give us a positive deflection, a positive wave, and we will see the details of these waves and intervals when we record the AVL. So now we are recording AVL. We are placing the active electrode here at point VL. and we connect this active electrode to the positive end of the galvanometer, and the reference electrode is kept at 0 and connected to the negative end of the galvanometer. So the impulse originates at the sinoatrial node and spreads to depolarize the atria. So now the polarization is moving in the direction towards the active electrode. So the needle of the ECG machine moves up, giving a positive wave. So it moves up and then back to the isoelectric line, giving a positive wave, because atrial depolarization is moving towards the active electrode placed at VL. This positive wave recorded as a result of atrial depolarization is known as the P wave. Then the impulse reaches the AV node and is delayed in the AV node, and when the impulse is delayed in the AV node, the needle of the ECG machine remains at the isoelectric line. Then the impulse spreads to the ventricles through the AV bundle of Hess and bundle branches, the right bundle branch and the left bundle branch, to depolarize the ventricles. The first part of the ventricle to get depolarized is the interventricular septum, and it is depolarized by the left bundle branch. Thus, the polarization of the interventricular septum moves from left to right. So, the polarization of the interventricular septum from left to right moves away from the active electrode, because the active electrode is here at VL. So this gives a negative deflection in the ECG lead termed Q wave. So Q wave is due to septal depolarization from left to right. Then the walls of the right and left ventricles are depolarized, and depolarization of the ventricular walls proceeds from the endocardial surface to the epicardial surface, from the inner surface to the outer surface, from the endocardial surface to the epicardial surface. So in the case of depolarization of the left ventricular wall, depolarization is moving in the direction of the active electrode, while in the case of depolarization of the right ventricular wall, depolarization is moving away from the active electrode, because the active electrode is here at VL. So what will this give then in the ECG? Will the ECG needle move up, giving a positive deflection, or down, giving a negative deflection? This is a very important question. We have known from the previous lectures that the left ventricle is 2 times to 3 times as thick as the right ventricle. Thus, the depolarization current of the left ventricle is 2 to 3 times as big as the depolarization current of the right ventricle. Thus, the ventricular activation, the left ventricular activation will dominate, and this moves towards the active electrode, giving a positive deflection, a positive wave. So the needle moves up and then returns back, giving a deflection above the isoelectric line. So it is a positive deflection termed R wave. The last portion of the ventricles to get depolarized is the pulmonary conus, is the part of the right ventricle where we have the origin of the pulmonary trunk, and when this happens, depolarization is moving in this direction away from the recording electrode, and this gives a negative deflection known as the S wave. So the Q wave along with the R wave and the S wave represent depolarization of the ventricle, ventricular depolarization, and we combine them together and we call them QRS complex. So the QRS complex is due to ventricular depolarization. And when the ventricles are uniformly depolarized, now the ECG needle returns back and remains at the isoelectric line. Then after the ventricles finish with depolarization, the ventricles begin to repolarize. Repolarization of the ventricles proceeds in an opposite direction to depolarization. In other words, repolarization moves from the outer surface to the inner surface, from the epicardial to the endocardial surface of the ventricles. So again, since the left ventricle is 2 times to 3 times thicker than the right ventricle, the repolarization current of the left ventricle will dominate, and this is moving away from the active electrode because the active electrode is placed here at VL. So ventricular repolarization then gives a positive deflection or a positive wave named as T wave. So T wave is due to ventricular repolarization. Now an important question arises, which is why atrial repolarization does not appear in the ECG? The atria repolarize at the same time when the ventricles depolarize. And since the ventricles are much thicker than the atria, the ventricular depolarization current dominates, and this is the current which is going to be seen in the ECG leads, and this current is seen as the QRS complex as we have just described. So we have finished with recording lead AVL, and we can record the remaining leads separately as I mentioned. However, for the convenience of the patient, we record all the 12 leads simultaneously at the same time, and this is a standard 12 lead ECG. These are the 3 bipolar limb leads, lead 1, lead 2, lead 3, and these are the unipolar limb leads, AVR, AVL, and AVF, and these are the unipolar chest leads, V1, V2, V3, and here we have the V4, V5, and V6. This is a normal ECG, and let's apply Einthoven's law to this ECG to see whether our ECG connection and the placement of the electrodes were correct. So this is lead 1, lead 2, lead 3. These are the P waves, P wave, P wave, P wave. These are the QRS complexes, and these are the T waves. So let's take a wave in lead 2 and measure the voltage of that wave. Let's take, for example, the T wave. So this is the T wave in lead 2, and this is the voltage. The voltage is on the vertical calibration. So this is the voltage of T wave in lead 2. If we measure the voltages of the T wave in lead 1 and lead 3 and sum up these voltages, the summed voltage would be equal to the voltage in lead 2, indicating that our ECG connection and placement of the electrodes were correct. This is again a standard 12 lead normal ECG. And now let's describe the ECG waves, intervals, and segments in more details. Let's define the voltage of these waves and the duration of these waves and these intervals in details. And before describing this, it is very important to describe the voltage and time calibration of the ECG. This is the ECG paper or the ECG display, which we see on the monitor or the computer, and it is divided into small squares and large squares. Each large square is composed of 5 small squares in the vertical direction and also in the horizontal direction. Each small square is equal to 1 millimeter horizontally and vertically. So let's take this large square and magnify it. So each large square is composed of 5 small squares horizontally and 5 small squares vertically. Each of these small squares is 1 millimeter horizontally and 1 millimeter vertically. The vertical calibration lines in the ECG paper or in the ECG display represent the voltage in millivolts. And as we just mentioned, one small square in the vertical calibration is equivalent to 1 millimeter, and 1 millimeter in the vertical calibration is equivalent to 0.1 millivolt. Thus, 5 small squares in the vertical calibration, which are equivalent to 1 large square, are equivalent to 5 millimeters, and these are equivalent to 5 multiplied by 0.01 are equal to 0.5 millivolts. In the horizontal calibration lines represent the time in seconds. The ECG paper comes out of the ECG machine with a speed of 25 millimeters per second. Thus, each second is equivalent to 25 millimeters, or is equivalent to 25 small squares. So, 25 small squares from here up to here, this is 1 second. Or 5 large squares is 1 second. So 1 second again is equivalent to 25 small squares. Thus, 1 small square in the horizontal direction, 1 small square, 1 millimeter in the horizontal direction, is equivalent to 0.04 of a second, because 1 second is equivalent to 25 small squares, and 5 small squares in the horizontal calibration are equivalent to 5 millimeters, or equivalent to 1 large square, and these 5 small squares or 1 large square are equivalent to 5 multiplied by 0.04, so they are equivalent to 0.2 of a second. So here we have again the calibration. So if 1 small square is equivalent to 0.04 second, 2 small squares would be equivalent to 0.08, 3 small squares will be equivalent to 0.12 second, and so on. And this is seen in this horizontal calibration in the ECG paper. So having described the horizontal and the vertical calibration in the ECG paper, and having known that the horizontal calibration represents time in seconds and the vertical calibration represents the voltage in millivolts, let's describe the ECG waves and intervals in more details. The P wave, what does the P wave represent? The P wave represents atrial depolarization. What is a normal P wave? A normal P wave has an amplitude, has a voltage which is equal to or slightly less than 2 millimeters. In other words, it has an amplitude or a voltage which is equal to or slightly less than 2.5 millimeters. So it has got an amplitude which is equal or slightly less than, each millimeter is equivalent to 0.1 of a millivolt as we described in the vertical calibration. And it has got a duration of less than or equivalent to 0.12 of a second. 0.12 of a second is equivalent to 3 small squares, because each small square in the horizontal direction, in the horizontal calibration, is equivalent to 0.04 of a second. So this is a normal P wave because its duration is about, yes, this is 1 small square, 2, less than 3 small squares, so it is less than 0.12 of a second. The QRS complex represents ventricular depolarization. And what defines a normal QRS complex? A duration of 0.08, 2 small squares, up to 0.1 second, 2 small squares and a half. So this QRS complex this is 1 small square, and this is half small square, this is half small square. So the duration of the QRS complex in this ECG lead is 2 small squares, which is equivalent to 0.08 of a second. So it is a normal duration of the QRS complex. Increased width of the QRS complex is characteristic of defects in the bundle branches or Purkinje fibers. If we have left bundle branch block, if there is a block in the left bundle branch or in the right bundle branch, the ventricles would take longer time to get depolarized, so we will have longer duration of the QRS complex, and the longer duration of the QRS complex is seen in the ECG as wide QRS complex. The T wave represents ventricular repolarization, and a normal T wave has the same polarity as the P wave. The P wave is a positive deflection, so the T wave is also a positive wave. The PR interval, this is the time interval between the beginning of the P wave and the beginning of the QRS complex. So it is the interval between the beginning of the electrical excitation of the atria and the beginning of the electrical excitation of the ventricles. A normal PR interval has got a duration of 0.12 of a second up to 0.21 of a second. 0.12 of a second is equivalent to 3 small squares, and 0.1 of a second is equal to 5 small squares. So let's see whether our PR interval in this lead is normal or not. So this is the PR interval from the beginning of the P wave to the beginning of the QRS complex. So how many small squares? So 1, 2, 3, 4, and if we add these, so about 5 small squares. So 5 small squares is equivalent to 5 multiplied by 0.04, equivalent to 0.2 of a second. So this PR interval is of normal duration. What is defined by abnormally prolonged PR interval is when we have a block of the conduction of the impulse in the AV node. And this is seen in the first degree AV block. So when the electrical impulses are delayed than normal through their conduction in the AV node, this would prolong the PR interval. On the other hand, a shorter PR interval than normal signifies the presence of an accessory pathway between the atria and the ventricles. So when we have an accessory pathway, for example, a bundle known as the bundle of Kent, when this bundle is present, the impulses would bypass the AV node and would go through this accessory pathway faster than normal, so the ventricles would be depolarized earlier than normal, resulting in a shortened PR interval. The QT interval, this is the interval between the beginning of the Q wave and the end of the T wave. So it represents total ventricular depolarization and repolarization. And the normal duration of the QT interval is 0.35 of a second. This electrical interval coincides with the contraction of the ventricles, because ventricular contraction lasts from the beginning of the Q wave till the end of the T wave. When the ventricles are depolarized, they are excited and they begin to contract, and their contraction lasts also during repolarization. And when the ventricles finish with the repolarization, when they finish with the T wave, now the ventricles begin to relax, diastole begins. So the QT interval thus roughly approximates the period of ventricular systole. The ST segment is the segment between the S wave and the beginning of the T wave, and during this segment no electrical potentials are measured on the surface of the body, and the ventricular muscle cells are in the plateau phase of their action potentials. So calcium gets in, releasing calcium from the sarcoplasmic reticulum, and then the ventricles contract. Lastly, let's define what is the normal sinus rhythm. The normal sinus rhythm can be defined using the ECG. So this ECG strip shows a normal sinus rhythm. Similarly, this ECG shows a normal sinus rhythm. And a normal sinus rhythm means, from the electrophysiological point of view, it means that the cardiac impulses originate in the sinoatrial node regularly at a rate of 60 to 100 impulse per minute at rest in normal adults. How is the normal sinus rhythm is seen in the ECG? The P waves are upright, P wave, P wave, P wave, they are all upright, and they are of uniform size and contour from beat to beat. So these are the P waves, they are all upright and of normal, uniform shape, uniform size from beat to beat. And each P wave is followed by a QRS complex, P wave, QRS complex. So the ratio of the P waves to QRS complex is 1:1. And all complexes are evenly spaced. So the time interval between this P wave and the subsequent P wave and the subsequent P wave and the subsequent P wave, these time intervals are equal. Similarly, the time intervals between the successive QRS complexes, these time intervals are almost equal. So all complexes are evenly spaced and the PR intervals are constant with normal range. So these are the criteria for a normal sinus rhythm in the ECG. And that's the end of this lecture. And here we have the intended learning outcomes again. And thank you very much for listening.